40, so the net change will be 40 in the negative direction. So where do we end up? We end up at 20. All right, so that area is really the change between shear from B to C. So that's how we came up with that 20. Guys, how would you be tested on the test, on the exam for something like this? They could just give you the shear diagram for that segment only. And they give you, of course, 4 choices and say which one is correct. Do you get the hang of it? Now, what happens at the point C? At the point C, please pay attention. There is a concentrated load of 60 kilonewton. Now, because of the graph here, that's easy to miss. My recommendation is don't miss it. So the effect of that 60 kilonewton, it's a concentrated load at the point C. So the net change in shear would be 60 kilonewtons in the negative direction because it is acting in the negative direction. So if you start at positive 20, the change is 60 in the negative direction. Where do you end up? At negative 40. Now tell me, as we proceed from C to D, is there anything between C and D that would change the shear, which would really, in this case, it's the summation of forces in the y direction to the left of the cut. Is there anything that would change the summation of forces in the y direction from C to D? The answer is no, there isn't. Therefore, the shear remains constant at negative 40. Now, at the point D, we have this concentrated moment or a free moment acting on the beam. Please remember, if you have a concentrated moment like that, a free moment, it causes pure rotation and it has no effect whatsoever on the shear. Therefore, the shear stays negative 40 all the way from C to E, to that support E. And then, of course, at the point E, look at the original beam. It's a 40 kilonewton going up, so it brings you back. From negative 40, it brings you back to 0. And this is what we expect, and we expect the shear diagram to close. So it comes back to 0. All right? Now, next thing I want you to do is to help me. This is the shear diagram, complete shear diagram. And the next thing I want you to do is help me draw the moment diagram. All right? Once again, and I hope that everybody is participating in this because it's important. And it's really not that difficult. All right? So from this, the left end, we're going to use the shear diagram to create the moment diagram. Now, remember, in order to get the moment from shear, what do we have to do to it? Integrate it. All right, so M is equal to the integral of V dx. All right, so ask yourself, what is the degree of the shear between A and B? What degree curve is that? You got it. It's a first degree curve. It was that line. All right, so a first degree curve, when you integrate it, it becomes a second degree curve. What does a second degree curve look like? Ryan, what's SFD? Is that a shear? I don't know what SFD is. All right, several of you are saying parabola. Yeah, second degree curve is indeed a parabola. So we would expect from A to B, from A to B, the moment diagram would be a second degree curve. Which is a parabola. What does a parabola look like? There it is. That's a parabola. That, guys, is a parabola. But I can also draw a parabola. I'm not going to try it because it's difficult to draw a parabola freehand. But it could also be a parabola on the top of the horizontal line. But this is the correct one because it has to have a negative slope. Now pay attention. The parabola that we have from A to B showing the moment needs to have a negative slope. It has a negative slope because the shear is negative between A and B. Please make a note of that. That's one thing that they will test you on the exam. All right. So from A to B, since the shear is below the x-axis, then the moment diagram needs to have a negative slope. What I'm showing here, this is indeed a parabola. It's a second-degree curve with a second-degree curve with a negative slope. All right. But on the test, they will ask you one other thing. All right. Yeah, Ryan and Alan, the shear force diagram will always have to close. If it doesn't, there is something that you've done wrong. All right. So here, look at that line. It's not very crisp, but that also, if you pay attention, that also is a parabola with a negative slope. And this is one that they do ask and try to see if you understand which is the correct one. Obviously, the first one is the correct one. And this is something that, let's go back. This is the correct one. But why? Why is this the correct and not the other one? Well, if you go to any reference book or let's say a strength of materials book or sometimes statics book, they actually show several pages of calculations and they prove to you which one is correct. But I will tell you the quickest way to do this. And I think Donald may have the idea. But yeah, Stephen also. But guys, this is what I will just give you a statement. I want you to write it down, and this will help you. The slope of the moment diagram, the slope of the moment diagram at any point is equal to the intensity of the shear at that same point. I'll repeat. The slope of the moment diagram at any point is equal to the intensity of the shear at that same point. All right? Now tell me, what is the intensity of the shear? Let me see if I can show this. What's the intensity of the shear at the point A? It's 0. I hope that you do agree that the intensity of the shear at the point A is 0. Then, based on the statement that I made, then the slope of the moment diagram at that point should be what? 0. All right? So tell me, between this parabola and the parabola below, which one has a 0 slope at the point A? The first one does. This one does. The other one has a slope other than 0. All right? So this is how you decide which end would have a 0 slope. See, with this one, guys, the parabola at the bottom, that's the one that has a 0 slope at the point B. And that's not what we anticipate. All right? So let's go back to this. This is the correct parabola. And then where do we get the minus 40? How do we know the moment is 40? Well, remember, when we integrate a function, we are finding the area under that function. Now, in this case, the change in moment. And please make sure you remember the word change. The change in moment is equal to the area under the shear diagram between 2 points. All right, so the change in moment between 2 points is equal to the area under the shear diagram between those 2 points. That's how I got the minus 40 kilonewton meter right there. Let's move on, guys. We need to move on. Okay, between B and C, what do you think the moment diagram is going to look like? Well, ask yourself, what is the degree of the shear diagram between B and C? It's a linear function like that. It's a first degree. All right. So the moment needs to be a second degree curve with a negative or positive slope, with positive slope. Why? Because the shear is above the x-axis. It's positive between B and C. Therefore, there it is. That's the second degree curve. It's a parabola with a positive slope. Now, the change in moment between this point and up here is going to be equal to the area under the shear diagram. Now, that area, you can convert it or divide it into a triangle and a rectangle. In fact, that's what I've done here. So that area is equal to 80 kilonewton meter. So 80 is the change in moment between B and C. So if you start from negative 40, the change is 80 in the positive direction. We end up at positive 40. That's where we got the 40. As you go from C to D, look, the shear is a 0 degree curve. Therefore, moment needs to be a first degree curve with a negative slope. Why negative slope? Because the shear is below the x-axis. Now, in this particular problem, this is very important because at the point D, what do we have? Look at the load diagram. At the point D, we have a concentrated moment equal to 120 kilonewton meter. That will introduce an abrupt change. It will introduce an abrupt change in moment at the point D. The question becomes, is that going to be an abrupt change in the positive direction or in the negative direction? In this case, and I'll tell you, there's only one way to decide, and that's going to be positive in this case. And here's what I'm going to tell you. Next time we meet on Thursday, when I cover mechanics of materials, I will have more to say about this subject. But for now, please remember, if you have a beam and you have a concentrated moment, like the one that we have here, somewhere intermediate to the supports. That means not at the support. It's not acting at the support, but somewhere between the supports. This is the rule. If that moment that is somewhere intermediate to the supports, if it is clockwise, treated as a positive moment. If it's counterclockwise, treated as a negative moment. In this case, it's clockwise. Therefore, its effect is going to be an abrupt change in the positive direction. So let's move on to the next slide. There it is. So the change is 120 kilonewton meter. You start from negative 40. The net change in the positive direction is 120, so we end up at positive 80. Then, as we go from D to E, it's a first degree curve with a negative slope because shear is negative, and that's what we get. All right, so this is the entire moment diagram. Let me ask you a question. They may give you this moment diagram and ask you, what is the maximum moment in this beam? So tell me, if I give you this moment diagram and I ask you, please tell me what is the maximum moment, what would you say? Okay, 80 kilonewton. Many of you, Arash, Paul, Brian, you are saying 80 kilonewton, and you're correct. No, Arash says 120. I don't know where you got that, Arash, but no, the answer is 80. It's 80. I think what he's doing, he's adding 80 and 40, but no, if this is the moment diagram, the designer will need to design this beam for such that it would resist 80 kilonewton meter. All right, now let me Let me see if I can get rid of this. If I can erase this, it would be good. All right. Now, for the sake